Welcome back to this short series on the fundamentals of control engineering. In the previous video, we introduced the Fourier and Laplace transform, and now we are ready to state some properties of these transforms. We will state them for the Laplace transform, but many of them will hold also for the Fourier transform. But before this, we need to mention something. So we have defined the Laplace transform x of s as the integral from minus infinity to plus infinity of x of t times e to the minus s t in dt. But actually, in signal processing and control theory, we are typically interested in signals that start at zero. So we can take the product of x times the Heaviside function, which we denote by a bold one of t. And this is basically equivalent as taking the so-called monolateral Laplace transform, which has as the lower integration extremum just 0. And this will be the transform that we will deal with in all that follows. I mean, this transform has a set of very interesting properties, and we can list some of them. The first is linearity, and this means that the Laplace transform applied to a linear combination of signals gives the linear combination of the Laplace transforms. Then we have a frequency shift property. Now, in the case of the Laplace transform, we are not exactly using a frequency, but we are using a generic complex variable, but this is still called the frequency translation or frequency shift property. So we have the Laplace transform of an exponential e to the alpha t times x of t, and this will be equal to the Laplace transform x in s minus alpha. This becomes a proper frequency shift property if alpha is a complex number, an imaginary number, and we take the special case of the Fourier transform. Then we have a property related to the time derivative of a signal, where if we take the Laplace transform of the time derivative of a signal, this is equal to s times the Laplace transform minus x in 0. And notice that this can be proved by taking a partial integration, and the fact that here we have 0 depends on the fact that here we have the monolateral transform. We also have a property related to time integration, where if you apply the Laplace transform to the integral from 0 to t of a signal, then this is just 1 over s times the original transform. Note that the last two properties are of paramount importance, and they're probably the main reason behind the popularity of the Laplace transform in control engineering, because they allow to transform the differential relations involving derivatives and integrals into algebraic ones involving multiplications and divisions times the complex variable s. Next property is related to the convolution product of two signals, and you can imagine that this property will be very important when dealing with linear systems. So we have convolution, and the Laplace transform of the convolution product of two signals, x and y, is just the product of their respective Laplace transforms. And you can imagine that this will make the solution of linear systems much easier than just computing the full convolution product. And as a reminder, we know that this product here, x of t star y of t, is defined as the integral from 0 to t of x of t minus tau, y of tau d tau. Finally, we have two interesting theorems, which are the initial and final value theorems. The first one states that the limit for t that tends to 0 from the right of x of t is the same as the limit for s that goes to infinity of s times the Laplace transform of the signal. And sometimes it's useful to combine this property with the property related to the derivation in time. So we also state that the limit for t that goes to 0 of the derivative of x is the limit for s that goes to infinity of s squared x of s minus s times x evaluated in 0. And finally, we have the final value property, where the value of x for t that now goes to infinity is the limit for s that goes to 0 of s times x, the Laplace transform of the signal. We can now list some examples of monolateral Laplace transforms. The first one will be the transform of the Heaviside function, 1 of t, and this becomes 1 over s. And we can also transform the Dirac's delta function, and we can do it, for example, by using the derivative in time property, and this will be 1. And actually it's s times the Laplace transform of the Heaviside function. We can also take the transform of polynomial signals, so we can take t to the n over n minus 1 factorial, and it will be 1 over s to the n. And here we're clearly taking the integral of the Heaviside function. Now remember, all these signals are multiplied times the Heaviside step, so this polynomial is only non-zero after t equals 0. Then we have the transform of an exponential, which is also easily found by using the properties of the Laplace function. And I encourage you to try to work out these Laplace transforms on your own. This will be 1 over s plus a. We are using the frequency shift property. And then we have the transform of sinusoidal functions. So the sine of omega t becomes omega over s squared plus omega squared, and the cosine, well, we can find this through the derivation property, so this will be s over s squared plus omega squared. And here it is worth to notice an interesting fact, that is that these Laplace transforms are not the same as the Fourier transforms. So if we restrict the Laplace transform to s equals I omega, we don't get the Fourier transform, which was a couple of Dirac impulses. And the reason why this is true is that the Laplace transform is not defined for omega, for s on the imaginary axis, because this transform has an abscissal convergence which is exactly 0. So for s less or equal than 0, this Laplace transform is not well defined. However, if you let the real part of s tend to 0, you will recover the fact that the Laplace transform goes to infinity for s equal to plus or minus I omega. Now, what happens if we apply the Laplace transform to a linear system? And what does it mean to apply the Laplace transform to a linear system? Well, we can write our system as x dot equals a times x plus b times u, and then we know that y equals c times x plus d times u. And we can apply the Laplace transform, which means applying it to both the right and left hand side of the equations, and this gives us s times the Laplace transform of x equals a times x plus b times the Laplace transform of the input, and y of s is c times x plus d times u. So we can actually find an expression for y as a function of u. And the way to do this is just taking x of s is s times the identity matrix minus a to the minus 1 times b times u of s, and y of s is just c times x, so c times s times the identity matrix minus a to the minus 1 times b plus d u of s. And if we actually look at this last expression here, well, we'll see that this is a complex function that links the input u directly to the output y. And we call this the transfer function of the system. And notice that since this links the input to the output, this is an input-output representation of our system. We don't need to know the state to write this down. Now, it's interesting to observe that if Si minus A is an invertible matrix, then we can write this down as C times the so-called cofactor matrix, which is transposed, times B, and this is divided by the determinant of S times the identity minus A. So this will be our y of s. So this here is our transfer function. And note that at the denominator we have we use this expression when dealing with the eigenvalues of the matrix A. So this is linked to the eigenvalues of A, as we have seen in one of the previous videos. So we expect that the modes the natural modes associated to the system, which are related to the eigenvalues of A, will play a role. And in particular, the eigenvalues of A will be the roots of the denominator of this fraction. Moreover, we observe that actually this has the form of a fraction. And for linear systems, this is a general rule. Every transfer function for linear systems has the form of a fraction, where the denominator of the fraction is the characteristic polynomial of the matrix A. Moreover, we observe that the C and B matrices here pre and post multiply this fraction, and they might be so that they mask some of the modes which come from this cofactor matrix, and this might give rise to observability or controllability issues. We will discuss this in a different video. Finally, we can also ask ourselves, what is the physical interpretation of the Laplace transform for a linear system? Well, we have seen that our linear system can be represented in the form x dot equals ax plus bu and y equals c times x plus d times u. And we have seen that we can integrate this formulation in time to obtain an explicit representation for our system, where x of t is the free evolution plus the convolution integral from 0 to t of e to the a t minus tau b u of tau, and y is c times x plus d times u. Now we have a third representation for our system, where we can write that y of s is c times s, the complex variable, times the identity matrix minus a to the minus 1 times b plus d times u of s. We have seen that we can go from the input state output representation of the system to this representation by taking the Laplace transform of the system. And we are now looking for a relationship between these two representations here. Let us write down the expression for y whenever the system starts from zero initial state. So we set x naught equal to 0, and we write y of t is c times, well, let us write the integral from 0 to t of c times e to the a t minus tau times b u of tau, and then we have the term d times u of t. Well, we immediately notice that this term here is basically this product here. And remember that the transform is linear, so this just transforms as d times the transform of u. But now here, what we have is a convolution product. So this would be the convolution product of c times e to the at times b. Let's see what this means in slight more detail. So let's consider the following example. We consider the linear system x dot of t equals minus x plus u. So this is a scalar system where there's only one natural exponential mode, which is e to the minus t. Now let's write down the free evolution for the system. And let us consider the forced evolution, so the case where x naught is 0 and we have some input. This is given by the integral of e to the minus t minus tau times u of tau d tau. And now let's choose u of tau equal to the Dirac's delta function. Now what we obtain, thanks to the sampling property of the delta function, is the following. X is the convolution product between the term e to the minus t minus tau times the delta function. And the sampling property just tells us that the result of this integral is the function multiplied times the delta evaluated in tau equals 0. So this is just e to the minus t. Now we recall the property by which the product of an exponential times a signal, when we Laplace transform, gives us a shifted Laplace transform. And so in this case, the Laplace transform of our first evolution will be given by, and let me denote this by x of delta to indicate that this is the first evolution under the effect of a Dirac's delta. But now, what if we take the Laplace transform of our system? Well, we have seen that the Laplace transform is given by y of s is equal to C, but in this case we are just looking at the state, so C equals 1 times S times the identity matrix minus A to the minus 1, but in this case A is scalar, so S times the identity matrix is just S, and A is 1. Actually it's minus 1, so minus A is 1, and we have 1 over S plus 1, which is exactly the same term we have just written for the first evolution. And then we have B, but B is again 1. And then we know that this must be multiplied times the Laplace transform of the input. But we have seen that the Laplace transform of the Dirac's delta is just 1. So what we have learned is that the Laplace transform of the system is nothing else but the transform of the first evolution of the system under the effect of a Dirac's delta, which is also called the impulse response of the linear system. And this is a completely general result, and it holds for any linear time invariant system. And note that we could approximate the Dirac's delta with some signal which is very narrow in time and has integral equal to 1. So what happens is that the delta function brings our system in a state which is in this case the amplitude of the Dirac impulse. And then the system evolves after 0 as its natural modes would command.